Hey, welcome. Today we're jumping into a really cool and super important idea from calculus. It's all about how we can guarantee 100% that there's a perfectly flat spot on a curve, just as long as it plays by a few simple rules. Okay, let's get right into it. So to get us started, let's just do a little thought experiment. Imagine you're out on a hike. You start at a certain elevation, you go up some hills, down into some valleys, but here's the key. You finish your hike at the exact same elevation where you started. So the question is, at any point on that trip, was there at least one moment where the ground was perfectly, completely level? I mean, your gut feeling probably says yes, right? It just has to be. If you went up, you eventually had to come back down to get to that same starting height. And right at the very top of that hill, that peak, or at the bottom of that valley, there had to be a point, even for just a split second, where things leveled out. Well, this whole idea is actually formalized in a really famous theorem in mathematics. It's called Rolle's theorem, and it's basically the official rulebook for finding these guaranteed flat spots. It takes our intuition and makes it rock solid and precise. And this isn't just some random theorem either. It's actually a critical stepping stone for proving the mean value theorem, which is one of the biggest deals in all of calculus. So what does it take? What are the specific conditions? Well, Rolle's theorem gives us 3 specific rules that a function absolutely has to follow for this guarantee to kick in. And you'll see our hiking analogy maps perfectly to the math. First, the function has to be continuous. That just means the path has no gaps. You can't just teleport from one spot to another. Second, it has to be differentiable. This means the path is smooth, no sharp, jagged corners. And third, f of a has to equal f of b. That's our hiking rule. You have to end at the same height you started.
Okay, so if you meet all 3 of those rules, and only if you meet them, Rolle's theorem makes a very powerful promise. It guarantees that there is at least one spot, we'll call it C, somewhere between your start and end points where the derivative of that function is exactly 0.
So what on earth does a derivative of 0 even mean? Well, geometrically, it's pretty simple. The derivative is just the slope of the line that's tangent to the curve at any given point. So a slope of 0 means that tangent line is perfectly horizontal. That's it. That's our flat spot, the mathematical equivalent of standing on perfectly level ground. Now, you might be thinking, do we really need all 3 of those rules? Are they all that important? Well, let's find out. Let's see what happens when we try to break one of them and see how that guarantee just completely falls apart. Okay, first up, rule 1, continuity. Look at the left side. You've got this nice unbroken curve. It starts and ends at the same height, so it has to have a peak, a flat spot. But on the right, what if there's a big jump in the graph? The function can get right back to its starting height without ever having to turn around and flatten out, so poof, the guarantee is gone.
What about rule 2, differentiability? A smooth curve, like on the left, has a really obvious flat spot at its peak. But look at the curve on the right. It's got a sharp, pointy corner, kind of like an absolute value function. And at that sharp point, the function isn't differentiable. You can't draw a single tangent line there, let alone a horizontal one, so again, the guarantee is broken.
And finally, rule 3, which is probably the most obvious one. The endpoints have to be equal. If you start and end at the same height, like the graph on the left, you've got to turn around somewhere. But if you start low and end high, like on the right, well, you could just go straight up in a line. There'd be no flat spot anywhere to be found. All right, that's enough theory. Let's actually put this theorem to work and see how it holds up in practice. We're going to take a function, run it through the rules, and then we're going to hunt down that guaranteed flat spot. So here's our challenge. We've got the function f of x equals x times the quantity x minus 1 squared, and we're only looking at the interval from 0 to 1. Our mission is to prove that Rolle's theorem applies here. So let's go through our checklist. Rule number 1, is the function continuous? Oh yeah, if you were to multiply this out, you'd see it's just a polynomial. And one of the best things about polynomials is that they are continuous absolutely everywhere. So rule 1 gets a big check mark. Next up, rule 2. Is it differentiable? Well, we gotta find the derivative first. After a little bit of the product rule and power rule, we find that f prime of x is 3x squared minus 4x plus 1. And guess what? That's another polynomial, which means our original function is differentiable everywhere. Rule 2, check. And now for the final rule. Do the endpoints match up? Our interval is from 0 to 1, so we need to see if f of 0 is the same as f of 1. Okay, let's plug in 0. We get 0. Now let's plug in 1. And because of that 1 minus 1 part, we also get 0. So yes, they're equal. Rule 3, check.
And there you have it. 3 for 3. Our function is continuous, it's differentiable, and the values at the endpoints are the same. That means Rolle's theorem is officially in play. It now promises us, guarantees us, that there has to be some number c somewhere between 0 and 1 where the derivative is 0.
So, the theorem says that point exists. Now for the fun part. Let's actually go find it. Let's solve for the exact value of c. Okay, to find c, all we have to do is take that derivative we found, 3x squared minus 4x plus 1, swap the x for a c, and set the whole thing equal to 0. That gives us a pretty straightforward quadratic equation, 3c squared minus 4c plus 1 equals 0. And lucky for us, this thing factors really nicely into 3c minus 1 times c minus 1 equals 0. Now, from that factored version, we can see two possible answers pop out. Either c equals 1 or c equals 1/3. So wait a second, which one is it? Are they both the flat spots the theorem was talking about? This is a really, really important detail. Let's think back to how the theorem was worded. It says there's a point c between a and b. In math terms, that means it has to be in the open interval, which doesn't include the endpoints themselves. Our value c equals 1, well, that is an endpoint. But c equals 1/3, that is definitely between 0 and 1. And that's our answer. The guaranteed flat spot, the value c that Rolle's theorem promised we would find, is 1/3. And just like that, we've seen the whole thing play out perfectly. We checked the conditions, the theorem made a promise, and we went out and found the exact value, c equals 1/3, right inside the interval where the derivative is 0. We have officially verified Rolle's theorem. So we've seen how this works for a nice, clean polynomial. But what about something a little messier? Here's a little something to think about. Could you use these exact same 3 rules to verify Rolle's theorem for a function like e to the x times cosine of x on the interval from -π/2 to π/2? The process is exactly the same. Go on, give it a shot. Thanks for tuning in.